Hello and welcome to today's lecture. In last class, we had discussed the normal distributions towards the end of last lecture. So, we will begin by briefly recapping what we had discussed. So, for a normal distribution, your probability density function f x has the expression 1 by sigma root 2 pi exponential x minus mu whole square by 2 sigma square, where x can have any values between minus and plus infinity. Okay. So, we had derived that for, so as you see that there are two parameters in this normal distribution probability density function, this is mu and sigma, and we had derived that for a normal random variable expectation of x will turn out to be mu and the standard or variance of x will come out to be sigma square. Also for a normal distribution, okay, because it is symmetric, okay, your mean, median and mode give you the same value, okay, are equal. Okay. Now, from this random variable you can convert it into a standard normal variable, which is typically given by this expression z is equal to x minus mu by sigma. If you do this, then you get f of, instead of f of x, you will have f of z, which turns out to be 1 by root 2 pi e to the power minus z square by 2. Okay. Okay. And in this case, the normal distribution, so this the regular normal distribution has parameters mu, mean mu, so this is your value mu, and variance sigma square. Okay. So, roughly 3x, so 3 sigma will mu plus minus 3 sigma will contain all your data. Okay. For this, for the standard normal variable, so this is written as the standard normal variable. So, this has mean of 0 and variance of 1. Okay. So, this will be centered at the origin, okay, and it will be symmetric. Okay. So, the cumulative distribution function is given by phi of x, okay, which is given by 1 by root 2 pi minus infinity to x e to the power minus y square by 2 dy. Okay. So, if you have any x, so probability of let us say x which is less than b can be converted to a standard normal variable is equal to phi of b minus mu by sigma. Okay. So, if x has mean of mu and variance of sigma square, then this p of x less than b is nothing but phi of b minus mu by sigma. Similarly, probability of a less than x less than b will give you phi of b minus mu by sigma minus phi of a minus mu by sigma. One more thing, because your distribution is symmetric, okay. So, let us say this is x and this is minus x, this is your origin. Okay. So, phi of minus x, which is this area, okay, will be equal to this. Okay. So, you can write phi of minus x as nothing but 1 minus phi of x. You can see it, visualize it from this plot. Phi of minus x is this area, phi of x is this entire area, and 1 is the entire area under the curve. So, 1 minus phi of x will give you this area, which is equal to this area. So, this is another useful expression to remember. Okay. Now, there is another interesting idea. Okay. So, if you have random variables x1, x2, x3 dot 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 xn, okay, which are all normal random variables, okay, with means of mu1, mu2, mu n and sigma 1 square, and this variance is sigma 1 square, sigma 2 square, dot sigma n square. Then for, let us say, if you have a variable x which you define as summation of xi, okay. So the moment generating function for this x will be phi of t is exponential of e to the power t x. Now let us assume also that these random variables are independent. Okay. So your moment generating functions becomes phi of t equal to e to the power t x. In last class we had derived that the moment generating function gives you the expression exponential of mu t plus sigma square t square by 2. Okay. So this is for single variable. Okay. So for this case where x is summation xi, I can write as e to the power t summation of xi, and e to the power t summation of xi can be written as e to the power expectation of pi of e to the power t xi, okay, where pi is pi of xi is I is equal to 1 to n. So pi is nothing but the product, that is, so this is e to the power t x1, e to the power t x2 dot. Okay. So I can take this product out and I can write down as pi of expectation of e to the power t xi. Okay. And for this I know that phi of t has gives you this expression. Okay. So this is nothing but pi of, okay, e to the power mu I t plus sigma I square t square by 2. Okay, and you have a product. Okay. So eventually you will get this phi of t as e to the power summation of mu I t plus sigma I square t square by 2. Okay. This tells you that for the random variable which is defined as the sum of these independent random variables which are normal distributions, okay, normal random variables, the mean, so x will follow a normal distribution with mean mu. Okay. So x will follow normal distribution with mean summation of mu I and variance summation of sigma I square. Okay. So let us consider an example where this concept might be very useful. Okay. So imagine you have rainfall, okay, the yearly rainfall, okay, yearly rainfall, okay, in a city is a normal random variable with mu equal to 12 centimeters and sigma equal to 3 centimeters. Okay. And you are asked the question, okay, what is the probability, okay, of rainfall for the next 2 years exceeding 25 centimeters. Okay. What you see here is that since the rainfall in a given year is a normal random variable and there is no correlation between the rainfall in a given year and the rainfall in the next year, so you can assume that the rainfall in each year is a standard normal variable and these variables are independent of each other. Okay. So I can write x1 is the normal random variable of rainfall in year 1 and x2 is similarly the normal RV of rainfall in year 2. Okay. So what we have been asked to calculate is the probability of x1 plus x2 greater than 25 is what we have been asked to calculate. So this is This is what we have been asked to calculate. Okay. So, now invoking the proof, the theorem that we just proved, that for a variable x which is defined as summation xi, okay, your mu, where xi's are normal random variables, your mu is summation mu I, and sigma square is summation sigma I square. Okay. So, if we use this particular idea, then what we should have is the variable x1 plus x2 should have mean equal to 12 plus 12, that is equal to 24, and variance, okay, equal to 3 square plus 3 square equal to 18. Okay. So, we want to calculate probability of x1 plus x2 greater than 25. Okay. So, I can convert this into a standard normal variable. So, let us say this is x. So, I can define x is equal to x minus mu by sigma, which is equal to x minus mu is 24, because this random variable has a mean of 24, and sigma of, so sigma square is 18. Okay. It is root of 18 is the sigma. Okay. So, what we can then do, okay, so probability of x1 plus x2 greater than 25 is nothing but probability of z greater than 25 minus 24 by root of 18. Okay. So, this is, roughly, if you look up the tables, the normal distribution tables, you will see this probability come out to be 0.4. Okay. We can ask another question. Okay. Let us take another question, okay, where what is the probability that, okay, that this year's rainfall exceeds that of next year, okay, by more than 3 centimeter. Okay. So, again, if x1 is for the normal random variable for year 1 and x2 is for year 2, then what we have been asked to determine is probability of x1 minus x2 greater than 3. Okay. So, once again we can use the previous theory and say that, okay, so the random variable x equal to x1 minus x2 will have a mean of 12 minus 12, which is equal to 0, okay, and a variance of 3 square plus 3 square equal to 18. Okay. So, just thus probability of x1 minus x2 greater than 3 is nothing but, okay, probability of x1 minus x2 minus 0 is the mean by root of 18 greater than 3 by root of 18, okay, is probability of z greater than 3 by root of 18. And this probability, if you look up the tables, it comes out to be approximately 25%. Okay. So, this is how you can make use of random variables, of multiple random variables which are independent of each other, and find out the probability associated with their sum or subtraction of the two random variables, so on and so forth. Okay. So, that brings our discussion of random variables or normal random variables to a close. I would like to discuss one more random variable, which is called an exponential random variable. Okay. For an exponential random variable, so your f(x) is defined as lambda e to the power minus lambda x when x is greater or equal to 0 and equal to 0 otherwise. Okay. So, I can see whether, so summation of f(x) would mean integral from 0 to infinity lambda e to the power minus lambda x by dx. Okay. I can take lambda out, and it is minus lambda x by minus lambda between 0 and infinity, which is equal to 1. Okay. So, this fulfills summation of probability is all probabilities is 1. Okay. I can determine the cumulative distribution function f of x, which is nothing but is probability x less equal to x is equal to 0 to x lambda minus lambda x dx, which turns out to be lambda 1 minus e to the power minus lambda x. Okay. So, your cumulative distribution functions is this, which means that probability of x greater than x will be equal to e to the power minus lambda x. So, we will make use of this probability slightly later. Okay. But for this exponential random variable, we can calculate the moment generating function. Okay. So, the moment generating function will be exponential e to the power t x is equal to 0 to infinity e to the power t x into lambda e to the power minus lambda x dx equal to, I can take lambda out, 0 to infinity e to the power minus lambda minus t into x dx equal to. So, this should give you a value of e to the power minus lambda minus t x by lambda minus t with a minus sign, and this is from 0 to infinity. So, this should give you a value of lambda by lambda minus t. Okay. So, phi of t is this, which would mean that phi of 0 t is equal to 0 is equal to 1, phi prime of t phi prime of t is so, this is lambda for minus 1 is equal to minus 1 square is equal to minus lambda by lambda minus t whole square. So, if I write it as phi prime of t, let us see, phi 0 is equal to 1. This can be written. So, you can write minus lambda by t minus lambda, t minus into minus. So, this can be written as phi prime of t can be written as minus lambda into d dt of t minus lambda whole to the power minus 1 is equal to minus and minus plus lambda by t minus lambda whole square equal to lambda by lambda minus t whole square. So, phi prime of 0, which is nothing but exponential of expectation of x, returns your value of lambda by lambda square equal to 1 by lambda. So, expectation of x gives you a value of 1 by lambda. We can accordingly do phi double prime of t. So, phi of t is gives you a value of lambda by lambda minus t. Phi prime of t is lambda by lambda minus t whole square. Phi double prime of t will give you minus 2 1 to lambda minus t whole cubed is equal to 2 lambda by lambda minus t whole cubed. So, phi double prime of 0 will be 2 lambda by lambda cubed is equal to 2 by lambda square. So, variance of x will give you e of, so this is e of x square, e of x square minus e x whole square equal to 2 by lambda square minus 1 by lambda square is equal to 1 by lambda square. Okay. So, variance of x gives you 1 by lambda square and expectation of x. Okay. So, this gives you expectation of x equal to phi prime of 0 is equal to 1 by lambda. Okay. So, one very important property of exponential distributions. So, this is slide number 9. So, one very important property of exponential distributions is its exponential distributions, okay, has this property that this distribution is memoryless. In other words, so let us take a case where we are considering the lifetime of a battery of a car or lifetime of a disk or so on and so forth. So, we would typically expect that if we know that the battery was operating okay as of today, it will probably depend. So, how much longer it will last will depend on how much it was operating now. However, in the case of a memoryless distribution, so you can write probability of x is the lifetime greater than t plus s given x is greater than t. In other words, it has lasted at least for t amount of time. What is the probability it will last for another s amount of time? So, this one would ideally expect to depend on this t, but this has the probability, this is does not depend on t, and this is simply probability of x greater than x. So, this is the memoryless. So, this is true for t comma s greater or equal to 0. Okay. So, this is the memoryless property of an exponential distribution, okay, and we will see why this is so. Okay. So, we can see we have calculated, we know that f x, okay, is given by 1 minus e to the power minus lambda x, okay, which would mean that probability of x greater than x is equal to e to the power minus lambda x. Okay. So, if probability, so which means that probability of, okay, x, so greater or equal to x is e to the power lambda x. So, probability of x greater than s plus t would simply be equal to e to the power minus lambda of s plus t. Okay, and this I can break it down, e to the power minus lambda s into e to the power minus lambda t is equal to probability of x greater than s into probability of x greater than t. Okay. Now, if this is so, then from this and this I can write down. So, probability of x greater than s plus t given x greater than t is simply probability of x greater than s plus t. Okay. So, you can simply write down this divided by this is, so probability of x greater than t plus s given x greater than t is equal to probability of x greater than s plus t by probability of x greater than t, and this gives me the value probability of x greater than s. Okay. So, this proves that this is the memoryless property of this particular distribution. Okay. And let us take one particular example to discuss how it is useful. Okay. Let us say the lifetime, okay, of a battery, of a car battery, okay, is exponentially distributed with average of 10,000 kilometers. Okay. If a person wishes to go on a trip of 5,000 kilometers, what is the chance that she will be able to do it without having to change the battery? Okay. Okay. So, what you are given is the average lifetime. So, average lifetime, okay, is equal to, okay, So 10 kilometers. Okay. So let us say if I put the average lifetime in units of thousands of kilometers, okay. So my lifetime is 10, okay, and I know the expectation. So expectation of this exponential distribution is 1 by lambda, and this is same as this 10, which would mean my lambda is 1 by 10. Okay. So I want to calculate probability of lifetime greater than 5, okay, which is nothing but 1 minus, okay, f of 5 equal to e to the power. So we know e to the power lambda into 5, okay, which is nothing but e to the power minus lambda times 5 equal to e to the power minus half. Okay. So this is what you see, that this distribution does not depend on to how long the battery lasted before, but it only depends on what is the average, and using that you can calculate the lifetime. Okay. With that we conclude our discussion of probability distributions. So across multiple lectures we discussed about binomial and special random variables, including the binomial random variable, the Poisson random variable, the uniform random variable, the normal distribution, and the exponential distribution. So from next lecture onwards we will start discussing about sampling distributions. Thank you for your attention.